We'll proceed in vector and commercial calculus. Vector and commercial calculus. So that is the discussion that we are pursuing. Vector and commercial calculus. Vector and energy calculus. What is the relationship between vector and energy calculus? Energy is a magnitude. Energy is a magnitude and direction. That is energy. So, if I am talking about vector, then certainly it is representing energy. So, vector and energy calculus, I am sorry, vector and commercial calculus. Wherever energy comes into the picture, then certainly commercialization will come into the picture. Vector and commercial calculus, vector and energy calculus. Now we are in a phase to discuss about the flux. Flux. If I have a velocity and it is passing through a surface, then what is the throughput volume per second will come out of the surface. If I have a fluid, if I have a fluid that is passing through a surface and fluid has a velocity, then through this surface, how much is the volume that is coming out per second? The unit of velocity is meter per second and unit of area is meter square. If I multiply this velocity with the area, it becomes meter cube per second. So if a liquid is passing through an area, then whatever liquid comes out from the surface is the volume, that is meter cube per second. So this is typically called flux calculation. How much is the flux through a surface when there is a velocity vector v? Then it is velocity vector dot product with the area vector. Velocity vector dot product with the area vector. That is the net flux coming out of it. So velocity vector dot product with the area vector. This velocity can be like this, hitting the surface at 90 degree. Or if I talk about the surface area vector, surface area has a vector and that vector is perpendicular to the surface. If this is surface, then surface area vector. If this is surface, then surface area vector can be like this in this direction. Or surface area vector can be like this in this direction. But it will be perpendicular to the surface. Now it is up to the surface. He has to decide that which one is positive surface area, where which direction surface area vector is. So someone can say, I have a surface and surface direction is like this. Okay, so typically it will be, if this is x-axis, this is y, I'm sorry, this is x-axis, this is y-axis, this is z-axis. In which direction surface is oriented? That talks about the surface normal, surface vector. If surface is directed in this direction, if this is the surface and it is directed anti-clockwise, surface direction is, I'm sorry, this is clockwise. Surface, the direction is anti-clockwise. Okay, surface direction is anti-clockwise. Take a right thumb rule, and if it is anti-clockwise, then that is the surface normal. So if this is the surface and it is anti-clockwise, it is same as like this. Okay, means it is anti-clockwise. Now I'm moving it the way surface I'm thinking about, anti-clockwise. Then this thumb, it talks about the surface direction. So if this is the surface, then around the surface line can be anti-clockwise or it can be clockwise. If it is anti-clockwise, then direction is this. If it is clockwise, then this is the direction of the surface. Now velocity vector is clear. Velocity is in one direction. Velocity vector dot product of the area vector is the net flux calculation. Velocity vector means magnitude of velocity, magnitude of the area cos theta. Here theta is 0 because this angle and area vector angle, the angle is 0. If angle is 0, then it is velocity vector magnitude and magnitude of the vector magnitude and magnitude of the area. Cos theta is 0, 1. Theta is 0, cos theta is 1. But if velocity is in this direction, then it in this direction, then it makes angle theta, theta from the x-axis. If this is x-axis, this is y-axis, this is z-axis, then it is making theta angle from x-axis. Okay, in that sense, it is velocity vector into area, a velocity vector magnitude into area vector magnitude, and then cos theta. If theta is 90 degree, then certainly no liquid is passing through this surface. Not possible. The liquid is going in this direction, and surface direction is this direction 90 degree. Cos 90 is 0. Nothing is passing through the surface. So this vector and this vector, area vector dot product with the velocity vector is the net flux calculation. Now question arises here is, what about if velocity vector is algebraic and area vector is algebraic? Algebraic in the sense, if I am saying this is my velocity vector, consider this is x-axis and this is y-axis for simplicity. This is x-axis and this is y-axis. This is origin. This is origin. Now, if I say velocity vector in this direction, I can say it is I plus j. I plus j is the velocity vector. And area is in this direction, then I can say it is I. So if area is 10 meter square, 10 meter, 10I. 10I is the area vector, or A, capital A, on top of it I can place one arrow mark, that is area vector. And V, small v, on top of it I can place an arrow mark. V vector dot area vector is the net flux it is passing. But V vector here it is I plus j. Consider V vector is algebraic vector, that is x minus yi plus xj minus yi plus xj divided by x square plus y square. Anything, algebra. Similarly, area vector is algebra. Okay, how area vector can be algebra? When I have a kind of a curve like this, and because of this curve, people may think that since it is passing through a hole, since it is passing through a hole will be in a fashion that there will be a kind of circumference, kind of a line kind of thing, and through that line one liquid is passing. So the surface will always be flat, not required. Means example we have already given, that like consider that there is a cloth that I sew it around the curve. Okay, so there is a cloth that I sew it around the curve. Okay, there is a cloth that I sew it around the curve. Now, if this cloth is sewed around the curve, then this area, what area we are thinking, this area, the surface area is not flat. If I pull it, I can pull it, and this I can pull it. The surface area is not flat. In that sense, or if I place like this, then area vector at the center is like this. Otherwise, area vector is different at different location. Area vector is different at different location. So here area vector is like, area vector will be momentary. At that point, what is the orientation of the surface? Surface orientation is different at different x and y. Okay, at different x and y. If this is x-axis, this is y-axis. If I take different x and y, depending upon that, area vector will be different. I mean, this is in yz plane rather than xy plane. I'm sorry. If this is x-axis, this is y-axis, this is x-axis, this is y-axis, this is z-axis, then this lie in yz plane. In that sense, or in that sense, if I, this is x-axis, this is y-axis. This flat what we see here, it is xy plane. If I take different xy here, then it will map here, and for those region, the area vector will be different. So area vector can be algebraic and velocity vector can be algebraic. How I can find area vector, that is a concern now. Now again, the net flux will be again velocity vector dot area vector. But now since it is algebraic, where there is independent component and dependent component. What is independent component? X-axis and Y-axis are independent component and Z-axis is dependent component. X-axis, Y-axis is independent component, Z-axis is dependent component. Z-axis is also called function over X and Y. F x comma y, function over X and Y, that is Z-axis. Or someone can say, if this is X-axis, this is Y-axis, then this is XY plane. This is XY plane. If this is XY plane, then this is Z-axis. Z-axis is dependent upon XY plane. Z-axis is dependent upon XY plane. XY plane is independent. In that sense, X and Y axis are independent to each other, and Z is dependent upon XY plane, or Z is dependent upon both X and Y. So we can say Z is function over X and Y. Z equal to F x comma y, function over X and Y, where X and Y are independent, and if we place a function over X and Y, it will produce a new value that is dependent upon X and Y, that is Z. So height is dependent upon XY plane. So that is the scenario of it. Now how we can calculate? Velocity vector I know. So if I see area vector is algebraic vector and velocity vector is algebraic vector, where there is dependent and independent component, then we cannot go with a direct dot product. Velocity vector dot area vector will not give the result because both are algebraic. Velocity vector dot d, that is differential. In integration, we have limit, we have integrand, and we have differential part. Velocity vector dot d of position vector of the area is the net flux that it will give it through. Makes sense? So we have two things. Okay, so I'll bring one kind of surface area vector. Okay, consider that I really have a surface. This is this is surface. Consider this is a sphere and it is centered at the origin. The center here, inside this, there is a center. This center coincides with the origin. This is x-axis, this is x-axis, this is y-axis, this is z-axis. In that sense, the center, this origin coincides with the center. Now, how we calculate the flux? What is flux? Consider that I place one charge, electric charge, at the center or origin. Then electric charge will flow through the surface because it flows in omnidirection. Electric charge wave. If there is an electric charge Q, if I place at the center, its wave, electric wave, will go in omnidirection all around. So it will pass through a full surface and it will go like this. How much is the wave that is passing through the full surface? Okay, then in that sense, we have to calculate the velocity vector that is coming out of the charge, velocity vector that is coming out of the charge, okay, that represent the wave, and dot product with the area vector. Dot product with the area vector. Okay, now that's why there is calculus. Now anyone, the way I was talking, taking out the clothes, because area may not be kind of flat. Now it will be anyone kind of a scratched head. How it's possible now? Okay, what is the equation of your velocity vector? Or the vector field that is coming out of the charge, vector field that is coming out of the charge. Consider it is q into xi plus yj divided by x square plus y square to the power 3 by 2. I mean q, that is the charge we have placed there. R vector, R is the radial vector, it is spherical coordinate system. R is radial vector. If charge is kept at the center, then all along this the electric field is flowing. Like a liquid is flowing, electric field is flowing all around it because of the charge. That is Q, that is the power of the charge into the R vector, all around R vector, divided by R to the power 3. Okay, that is it. So consider that is a velocity vector dot d of area vector. If it is calculus now, it is algebraic vector. D of area vector. But this is what is mentioned in the book. D of area vector, but it is wrong. Velocity vector dot area vector, that is actual flux. Velocity vector dot d of position vector of the area, that is actual flux. Velocity vector dot d of position vector of the area. What is position vector of the area? From the center of it, if I draw a line, consider there is a point here called P. From center of this to the P, I draw a line. P represents the area. P represents the area. P is any point on the area. That point is x comma y comma z. That point is x comma y comma z. From center, if I draw a line, then that is position vector of the area. That is xi plus yj plus zk. Now the flux calculation is velocity vector dot d of position vector, that is d of xi plus yj plus zk. So that flux is velocity vector. If v is the velocity vector, then we can say v1i plus v2j plus v3k. Okay. In the case of charge, v1 is qx by x square plus y square. Q r vector divided by r to the power 3. R I can say as xi plus yj plus zk. In that sense, r to the power 3 will become x square plus y square plus z square to the power 3 by 2. So the v1 vector will be qx by x square plus y square plus z square to the power 3 by 2. v2 will be q into y by x square plus y square plus z square to the power 3 by 2. v3 will be q into z by power 3 by 2. Now dot product d of xi plus yj plus zk. It will become v1 dx plus v2 dy plus v3 dz. That is the flux integration over the full surface. Okay, that is the flux, but no one can crack it. In reality, this is just abstract notation of the flux anyone can think of. But in reality, no one can calculate it. How to make it calculable? Okay, so what is the v vector dot d of position vector or v vector dot area vector? That is the flux. Area vector in terms of integration is become d of position vector. D of position vector. Now let's think from the 2D perspective. We have solved it in 2 dimensions already. So in 2 dimensional, if I have a force vector and there is a displacement that is have I brought one kind of ring kind of thing. Let's see if it goes inside it. Okay, more or less it goes inside it. So consider that there is a kind of item that is moving in a ring kind of fashion. There is an item that is moving here in a ring kind of fashion. It is should be very smooth. Okay. Now this item is moving from one location to other location because of this force field. If this force field is moving this item from this location to this location, how much is the work done? Force into this much displacement. If I see this displacement, force into this much displacement is the work done or energy, or force vector dot displacement vector is the energy, or force vector dot d of position vector. This, if I take any point on this curve at x comma y, and there is a position vector that is xi plus yj, force vector dot d of position vector xi plus yj, d of position vector, d of position where y is dependent upon x. If it is a circle, then it is x square plus y square equal to a square. Y equal to square root of a square minus x square. Means y is dependent upon x. Y equal to square root of a square minus x square. Y is dependent upon x. Okay. If y is dependent upon x, then force vector dot d of position vector. Position vector is xi plus yj. I can write xi plus fxj, or d of position vector I can write a d of dp by dx, because there is only one independent component x. So p can be dp. D is integral. D is differential inside the integration. D force vector capital F. On top of it is arrow mark. Force vector dot d of position vector. Position vector can be written as p, on top of it there is arrow mark. That is same as dp by dx into dx. dp by dx into dx, same thing. Now p is xi plus yj. That is same as dp by dx means xi plus yj will become I plus dy by dxj, where y is a function of x. So y I can represent as a function of x. So it becomes I plus dfx by dxj whole multiplied by dx, whatever is come. If it is circle, then it becomes I plus y is square root of a square minus x square by dx cross dx. So I plus minus x by square root of a square minus x square into dx. Now it becomes dx plus minus x by square root of a square minus x square dx. Okay, now so dxi minus x by square root of a square minus x square dxj. Okay, that is the differential part would become force vector. I can write as f1i plus f2j dot product. Full will become f1 dx minus f2x by square root of a square minus x square dx. Everything comes in dx. Just integrate over one point of x to another point of x. You get the energy calculus. Let's try same thing calculating the flux. If you try calculating the flux in similar way, then we have velocity vector dot d of position vector, where position vector is xi plus yj plus zk. Now, if I position vector xi plus yj plus zk, I can write as dp by dxy plane. Because xy are there, the independent component was x and dependent was y. Here independent component is xy plane, x-axis, y-axis, both are independent. So xy plane, this is our proof. You won't get anywhere else. So dp by dxy plane into dxy plane, same. So P is xi plus yj plus zk by xy plane by d of position vector by d of xy plane into d of xy plane. The d of xy plane, the numerator what we are seeing at the end, that will become dx dy, dx dy. And here d of position vector by d of xy plane, how it would go ahead now, that is a question mark. D of position vector by dxy plane. Position vector is xi plus yj plus function over x and yk, because z, that is height, is function over x and y only. So if velocity vector dot d of xi plus yj plus d plus fxyk by dxy plane into dxy plane. Okay, what is d position vector by dxy plane? That we have to calculate. Earlier it was easy. I remember for the 2D, position vector was xi plus yj, where y was dependent upon x. Just substitute it. So now if I say like this, then we did dp by dx into dx, and p was xi plus yj. Dxi plus dx become I, plus d of yj by dx become dy by dxj. Y was square root of a square minus x square, it become minus x by square root of a square minus x square j. If you multiply by dx, it becomes dxi minus x by square root of a square minus x square dxj. Now similarly, here how I can do dp by dxy plane, that is under question mark. How we can proceed dp by dxy plane? Does anyone has the answer? dp by dxy plane. Now I have p as position vector. Okay, I have P as position vector. If this is centered at the origin, if this is centered at the origin, then I have any point P here. From the origin, if I draw a vector, that vector is P vector, and this is a surface. Earlier we took in this curve, and from center I draw a vector, and that point was P, but that was a curve. Here this P point represents a surface. Now, no, but it is something like, but we know circle. Okay, someone would say, I don't know about surface, but I know circle. Okay, you know circle, right? Okay, let's cut in into two circles. How I can cut into two circles? Okay, if this is the point, this is x-axis, this is y-axis, this is x-axis, this is y-axis, this is z-axis. This is centered at the origin. Now, if this is the point P, let's cut in xz plane. If you cut in xz plane, it will become a circle. Now, if you cut in yz plane, it will become again a circle. Why we are cutting two times? Because there are two independent components. One is x and one is y. Here, independent component was only one, that was x-axis. Now, if I cut this sphere in xz plane, in yz plane, and in xz, so this is xz plane circle. If I cut like this, it becomes a circle, that is in xz plane. It will be filled though, it will not be whole one, filled though, but that will be a circle, and that is in xz plane. Another circle will be in yz plane. If this is in xz plane, let's differentiate it with the x. So where is your P position? P is here. This was a sphere. There was a point P. Touching the point P, I cut like this. Touching point P, I cut like this. If I cut like this is the point P. And if I cut like this, that same point is P is here. If this is P, then what is dP by dx? Hope. If this is the P, then what is dP by dy? Now it makes sense, right? If I calculate dP by dx, what if I have a, what is P? From center, if I draw a line, it is a position vector. Position vector is xi plus yj, where y is constant now. Because if I make a slice in xz plane, at every slice y will be some constant, x is variable and z is variable. Whereas if I make slice in yz plane, then every moment one x will be constant, but y and z will be variable. So if I'm talking about xz plane, then it is xi plus yj plus zk. Y is some y which is constant. I can take y as 0 also when I cut it along the x-axis on y-axis. So xi plus zk, something like that. Then if I do dp by dx, now in 2D, if I have a position vector like this, if I calculate differential vector of position vector, if I differentiate the position vector, it will result in another vector that will be tangent at that point. That is the inherent nature of differentiation of a vector. If I have a position vector, if I differentiate the position vector, it will result in another vector. That vector will be tangent at that point P. P is position vector that will tangent at point P. Please watch our previous video. Many times we have proved it, that how it will be tangent at that point. So anyway, now I have two circles. One is in xz plane, one is yz plane. dp by dx, if I calculate, I get a tangent surface like this, tangent vector like this. If I calculate dp by dy, then I get another tangent like this, but they are tangent at point P, same point. Now, hope, let's proceed. Now, if I if this is the point P and it is centered at the origin, and if I say this is, if I cut like this is XZ cut, and if I cut like this is YZ cut. Now dP by dx is tangent at this point in XZ plane. dP by dy is tangent at this point in YZ plane. In that case, if I do dP by dx, that is this vector, and dP by dy, if I do cross product of these two, dP by dx cross dP by dy, then it will become a surface vector. For two position vector, two vector, if you calculate cross product of it, it will give you the area between the position vector, something like parallelogram. Two vector need not be perpendicular to each other. If I leave this and it drops on my leg, then training is not possible. Okay, consider I have a vector like this and a vector like this. If I do cross product of these two vectors, then it will calculate the area between this vector. This vector, how much is the area? That is rectangle. And cross product has a direction, so that direction will be perpendicular to this area. That direction will be perpendicular to this area. Okay, like this. If these two vectors are not at 90 degree, still it will give the area. That will be the parallelogram what it forms. That parallelogram area will give. And again, the net vector direction will be perpendicular to the surface it is forming. So if I am talking about dP by dx, if I am talking about dP by dx, that is this vector, dP by dy is this vector, then cross product will give the area vector, and direction of the area vector will be at that moment what is the perpendicular to it. So everywhere dP by dx cross dP by dy vector will be different. Depends upon what was the algebra we had taken for P. But P is constant xi plus yj plus zk. No, z is variable here. Z is function over x and y. So it will be a function, pure function, and it will be changeable with different x and y. Anyway, what we had seen calculating the volume, calculating the flux, velocity vector dot d of position vector. It is same as velocity vector dot d of position vector by d of position vector by d of xy plane into d of xy plane. Now d of position vector by dxy plane can be written as d of position vector by dx cross d of position vector by dy. Same thing. dp by dx cross dp by dy is nothing but the it is nothing but the d of position vector by d of xy plane. It is understandable now that dp by dx cross dp by dy, cross is simple multiplication only in vector form. So denominator is anyway dx dy, dxy plane. Top is p only. So dp by dxy plane, d position vector by dxy plane, where position vector represents area, dp by dx cross dp by dy, the vector that we are seeing, that also represent an area. It is not exactly same because we are dividing it by dx and dy. Okay, so to kind of compensate, we are multiplying with dx and dy also. So it is all right. So the d of position vector, actually d of position vector, d of position vector should result into area vector. That is the scenario. D of position vector should result in area vector. In similar fashion, like D of position vector resulted in the displacement vector. Force vector dot D of position vector is a net energy calculation. D of position vector resulted in another vector, D of position vector, D of position vector resulted in another vector, and that vector D of position vector resulted in another vector, and that another vector was displacement vector. It is along the tangent along the displacement. Similarly, the, if I say velocity vector dot d of position vector is the net flux, means d of position vector should be area vector. D of, if from the center, if this is position vector that represent area, then d of position vector should talk about the area. Okay, if it talks about the area, d of position vector talks about the area. Here, d of position vector talks about the area. So what we did is that d of position vector, so if position vector is xi plus yj, then it will result into dxi plus dyj, or dp by dx is actual differentiation. Then I multiply by dx again to have the normalization. D of position vector results in the displacement vector. D, how I can calculate D of position vector? D of position vector, if I want, then it is same as dp by dx, multiply it by dx. Similarly, if I want D of position vector in flux calculation, then it is how I can calculate differentiation of position vector. I have to differentiate with something, right? Then only I can say it is differentiation of something. Otherwise, we can plainly say D of position vector in surface region is dxi plus dyj plus dzk. That is the area vector. That is velocity vector dot dxi plus dyj plus dzk, or velocity vector is v1i plus v2j plus v3k. The net flux is v1 dx plus v2 dy plus v3 dz. Or otherwise, if I want full-fledged differentiation, then dp by dxy plane into dxy plane. This is the proper differentiation. Same thing. Now dp by dxy plane. Now if I go even minute and going through the calculation of actual area, then it becomes dp by dx cross dp by dy. Means dp by dxy plane becomes dp by dx cross dp by dy. Okay, then what is net area vector? The net area vector is dp by dx cross dp by dy dx dy. Same thing that we got here. What is your displacement vector? dp, or dp by dx into dx. That is dp is xi plus yj. Then it is d d it is I, dxi by dx is I plus dy by dxj multiplied by dx, same as dxi plus dy by dx into dxj, or dxi plus dyj, same thing. Similarly, in the flux calculation, the velocity vector dot d of surface area position vector. Surface area position vector is d is xi plus yj plus zk. D of xi plus yj plus zk is dxi plus dyj plus dzk. If velocity vector is represented through v1i plus v2j plus v3k dot product, full it will come as v1 dx plus v2